Okay, so this work was completed by myself and Claudio from the University of Manchester and Simon and Peter from Axo Nobel, along with a lot of help and input from the other members of the SUSCORD project. So just a brief introduction at kind of what are anti-corrosive paints, at least in terms of what are the paints that we're interested in. We're interested in the organic coatings that are applied to metal to stop corrosion and have many applications from consumer packaging up to the aerospace sector. And these can get damaged or can degrade, and then the metal underneath can end up corroding. So in the UK, corrosion damage costs approximately £65 billion per year, directly contributes over £11 billion to the economy, and supports manufacturing worth more than £150 billion. So if we can improve these coatings, then we can really have a big impact. So specifically, we're interested in active corrosion protection coatings. So these consist of a polymer matrix loaded with corrosion inhibitors. There's my little schematic here. So our coating, we've got these inhibitor particles in here with bits of filler as well in between. If the coating gets damaged, show here, there's some like scratch, then water can get into this area and corrode the metal. So when that happens, the water comes in contact with our inhibitor particles, they'll dissolve and leach out of the coating. And when they come into contact with the metal, they'll form a protective layer on that exposed surface. So these corrosion inhibitors can be, for example, chromate or lithium salts that are soluble in water. And then as we expect them or hope that they will be touching the different particles, when the first one is exposed to water and dissolves, it then exposes the one behind it to the water, and then you end up forming this pore network throughout your coating. So there's a few things to consider. Chromate salts have better performance, but are worse for the environment. So we no longer use chromate salts. We want the coating to prevent the transport of water whilst allowing the transport of the inhibitor. By this we mean we don't want the particles, we want the particles to be kind of connected so that once it's damaged and one starts dissolving and diffusing, you have that knock-on effect and create this pore network throughout the coating. But we don't want that to happen too much, and then you end up creating a network throughout the coating the water can go through, and then it can reach the metal surface in another spot. So we've got to kind of balance those two things. And the mechanism for this, how the transport of the inhibitor, the formation of the protective layer, it's dependent on many different factors that are difficult to isolate experimentally. So that's why we're taking a modeling approach so that we can kind of try and find a bit more information about what's going on to aid the design of these coatings. So our aims are to use more environmentally sustainable materials and then aid the manufacturing process to reduce time to market and increase the performance of these coatings. So kind of long term, I'm looking at modeling the formation of the protective layer as well, using X-ray tomography data from real coatings, and then kind of, and with this modeling of this pore formation that I'm going to talk about today, to kind of combine those all to form a digital twin of a corrosion protection coating, which will be a numerical tool for the rational design of new products. But for today, I'm just going to focus on my current work, which is modeling this diffusion and dissolution and the formation of these pore networks. So here's my simple kind of model. So I've got the coating on the left-hand side. There's been some scratch or some damage, and so water's got in on the right-hand side. I have the polymer, which I presume there is no transport through and doesn't move or doesn't dissolve. And then we have some salt or inhibitor that is going to dissolve. I'm solving just for the diffusion equation in the liquid phase. And then I move my salt interface S. And with this equation, so this equation is essentially just calculating how much has diffused from that salt interface in a certain amount of time, and then calculating kind of how much space that salt took up, and so how far our boundary moves corresponding to that. And so my boundary conditions are just the concentration is the saturation concentration on that interface, and there is no change in the concentration over any other boundary. So with this, we're essentially assuming that the diffusion is a lot slower than the dissolution, so that we don't need to take into account the dissolution rate. It's just always going to be the saturation concentration. And that is something we're also looking into but it's quite simple. It's just a change of what these boundary conditions are, so it doesn't actually change the model that much. So I then non-dimensionalize this. So we introduce some value A. So that could maybe be like the typical diameter or size of one of these inhibitor particles. So I place X with A times X hat. So X hat is non-dimensional. So A could be 10 microns, say. And then X hat is just some number that you're going to multiply A by. So we do the same for the concentration. So we scale it with the saturation concentration, and C hat is non-dimensional. T becomes A squared over the diffusivity coefficient, and T hat is non-dimensional. And then we have this sigma, which is the ratio of the saturation concentration to the salt density. When you substitute these into these equations and rearrange them, you get these. So here I've dropped the hats. So these are all on non-dimensional variables. So now we can just work with these, and our boundary condition becomes C equals 1 on the interface. So now our concentration just varies between 0 and 1, and then to get it back in terms of like the real world, you times it just by your saturation concentration. So the advantage of this is that I can do one simulation and get an answer, and then if you want to know if A is 1 micron or 100 microns, I don't need to do that simulation again. You just times all your sizes by that value, and the same for the saturation concentration. And what this shows is our model is actually independent of the diffusivity coefficient. The diffusivity coefficient will only affect the time it takes for that to happen. So now we've got our non-dimensional system. We're going to solve this numerically. So most of my work has been making this or developing this moving boundary model to solve this. So I'm now going to introduce an R. So R is going to be a series of points. So I'm going to set up a mesh, which I'll show in a moment. So I'm going to have a series of points along this boundary, which I'm going to call R. And then I'm going to introduce another vector A. And if the point in R is on the salt interface, alpha is going to be a 1. If it's not, it's a 0. So that when you do your calculation for how you move R, if alpha is a 0, it's not going to move. So this is the new position of your point, is the old one plus some calculation based on this equation. So I'm just going to kind of go into a little bit more detail about that and try and explain my model now, my numerical model. So I'm using a finite elements package called Phoenix, and then we're using a time-stepping moving mesh algorithm. So hopefully I'm going to be able to demonstrate this. So we'll start with my simple example. I'm actually not going to start with this because there is a little bit more to it when you first initiate it. So I'm going to show you it when it's moved already a little bit. And then we can see my mesh. So anywhere where these kind of the lines connect, that's a node or a point. So we can see I have a lot more points, a much higher resolution on the moving boundary, so that I get high accuracy. As we move away from this more into the water, I can use less points and bigger elements to decrease my computational time. So I'm just going to concentrate on this area here, and then I'm going to make a Pore attempt at drawing that by hand. So this is the idea of, so I have my R vector, so it saves all the points on this boundary in order, and then I've shown in green if it's got an alpha as 1, and pink if it's got an alpha as 0. So we have our kind of some solution. So we increase time a tiny amount and solve for our new concentration. So everything should go a little bit pinker. And we then solve for where our boundary should move. So based on how much is now diffused from this boundary, we can calculate where these points should move to. Sometimes, especially on the side, the points want to move outside of where the salt is. And that obviously can't happen, because that means we've dissolved some part of the polymer, which we haven't. So we need to find out where that point should be, and while conserving mass. So when we did this, when we solved for where these new points are, we're essentially solving based on when we solve for our concentration, how much mass of salt has dissolved, which is the same amount of mass that this area covers. So we need to move this point onto the boundary, maintaining the area of this. So we can split it into triangles, and then use, I think it's quite a cool rule with triangles, that if you take a triangle and draw a parallel line to these 2 points passing through the third point, and then create another triangle between these 2 points at any point on this line. Those 2 triangles will have the exact same area. So we use that and find where that parallel line intersects the boundary of our salt, and then that's where we're going to move that point to. So what I should point out when I'm doing this, what I'm showing here in yellow and the grey doesn't exist in my simulations. I create where the salt is first, I have some structure, and then I only have the water phase as my mesh. So each time I move these points, I then need to say, does that point exist in the salt in my original start? And then I'm only ever dealing with the red and blue coloured stuff, and then comparing it to the where the salt should be. So now we know where the points should move to. We move them, except this has now stretched and distorted our mesh, which we don't want. And certainly as we continue this, it's just stretch and stretch. And that's not good for finite element methods. You want to kind of maintain your triangles. So we don't want that. And we've also lost kind of resolution, kind of the accuracy of mapping the side of the salt here. So what we do is we add a new point in there, decide if it's going to be a 0 or 1. We have to calculate knowing kind of where it is. Say if this point's kind of going further up and this point starts coming further down, we need to add points in between. We always maintain high resolution. So we take our vector of all these points. Now we know their new position, and create a new mesh. So we essentially connect all those points up, and with our water domain, and create a new mesh, and the Phoenix will just put all the interior points wherever they need to be, and we interpolate our solution onto them, so that we end up maintaining our accuracy on the boundaries, and we now have a much more uniform mesh. And then we just repeat that process every time. And we're using very small time steps, so it's a very, very tiny change each time. So that's kind of basics of the numerical model. So we just see that in action. So at some point we have this solution. We can always draw around the boundary, set if alpha is 0 or 1, and then move the green parts and not the pink parts. And we can see that moving here. And then we can measure how much mass has leached out into the main body of water. Because kind of that's what we're interested in. How quickly does that happen? So that's kind of a simple example. Now, we don't expect these particles to exist on their own. We expect there's going to be some kind of connection to form this Pore network, but they might not connect, in a line. They might go in different directions, so that now our moving boundary needs to be able to split and move in different directions. This isn't a problem. Again, we can draw around our boundary, this R vector that we're tracking, and that alpha vector just tells us if you're moving or if you're not. And it doesn't matter if we've got different, different kind of parts of that. And again, we can watch that happening. And what you'll notice here, as it's this area is going to start dissolving quicker. You can see it's kind of moving faster. This is because there's a larger space here to diffuse through, whereas this is kind of causing a bottleneck kind of effect. And if you watch carefully the graph as that finishes, it's really hard to see, but there's a slight kind of kink in the graph. Once this is finished diffusing or the dissolving, it's then limited by the kind of how fast this can dissolve and diffuse, and it's got a smaller gap. It's got a kind of a smaller dissolution rate. So these are the kind of things that we're interested in, finding what are the effects of these different things. If you have a big particle here, great, it's going to diffuse really quick. It's got a big boundary to the water. If you have a big particle here, but only a small hole connecting it to the next one, you're kind of losing that advantage. So we want to know, do you want lots of big, or less big ones, or lots of little ones? So that's the type of thing we're interested in kind of investigating. So our next problem is what happens if you have now a particle joining the other two? Now we need to be able to rejoin this moving boundary, which is a little bit more tricky because now we have two boundaries. So our previous method doesn't work for this. So I'm going to briefly kind of try and explain what we do here. So we take a solution as it's nearing that point. So we've got one continuous boundary as before. We zoom in and recall that this is actually a series of points. I haven't worried about green and pink here because it doesn't matter for the what we're about to do. And the idea is once these points kind of get within a certain distance, i.e. if I was to solve in the next time step, the points was essentially going to pass each other, and we can't have that. We need to change how our boundary connects. So instead of it being connected that way, we want it to connect that way. So what we do here, because we've got all these points saved in order, we basically say, okay, if you're now 2 points are within some very small distance, find where those points are. All the points in between those in our vector, remove from our vector. And then now our vector goes from here up here and round. I then leave an empty cell in my vector and then put all those points in afterwards. And then when I'm making my new mesh, my method knows connect all the first points, all the points up to that empty cell, connect it to the water domain. That's my total mesh. Whatever comes next is a hole, connect all those up and remove it from that mesh so that we end up with the, sort of creating that hole. And then if we have another hole, we just create another empty cell, put in whatever the next points are and keep removing that. So again, we can see that working here, just a simple one. So I should have sped up this video. And then they connect. So now the advantage is when these two finish dissolving, this now can go either way. It's like you don't decrease your dissolution rate so much. Okay, so moving on, we expect not only to be there to be one kind of inhibitor touching where the water is kind of where the crack is, where the water's got in. We can have multiple inhibitor particles touching the water, connected to other ones, rejoining, and particles that aren't part of the pore, going to be part of the pore network. But our method can do all of that fine now. Any number of kind of starting or kind of opening points, any number of kind of splitting, rejoining. And so this is kind of all the development of the numerical model that we're using. So we don't just have to use circles. I've just done that because it's easy to put in a load of circles to create my kind of starting picture. We can look at any different shapes, any different sizes, distributions, so we can start exploring how these different things affect the dissolution rate. And anything that isn't touching doesn't get dissolved. So I've then moved on to using what's called a Gaussian pore space. So the idea here is you take some grid, so I'm using in X 0 to -1 and Y 0 to 1, and then apply a uniform random distribution over that. And then to that uniform distribution, a Gaussian function, which essentially kind of smooths it. And that's what this is showing. So you've got numbers between 0 and 1, and you've got this kind of topography kind of up and down. You then choose some value. So for this, I'm choosing a half, and I'm going to say anything that's above a half is salt, anything less than the half is polymer. So then you color that yellow and gray, and essentially just squash it down flat, and you get the picture on the right-hand side. So now we've created this kind of random pore network. So we can choose different values. Obviously, if you choose a smaller value, you're going to end up with more salt, more yellow, higher value, more polymer. Because it's the way the Gaussian function works, a half does mean that exactly half of this is salt and half is polymer. So it's quite convenient. And we have this value lambda. So the smaller lambda is, the kind of less smoothing. So the more kind of disjointed the network is, or kind of more smaller kind of channels we're creating. The larger lambda is, kind of the more it's kind of collected together. So kind of like smaller particles, bigger particles. And again, all these have used this half. So half is salt and half is inhibitor. So the idea now is to use our method, which can solve over this, and start taking these pore spaces or pore networks and characterize them in terms of like volume fraction, tortuosity, and then compare how the dissolution rate compares to these characteristics. So essentially simulate loads of them and then compare kind of how these pore network characteristics compare kind of using statistical methods to the dissolution rate. And then we can, from those, we can kind of relate those to manufacturing parameters, such as like particle size and distribution, with the idea being then, if you create some, or you know how some kind of coating, how it's going to perform, we actually don't need to do the simulations. We should already know, if you then characterize that in your kind of manufacturing parameters, we can link that back to our pore network characteristics and already be able to infer how well that coating is going to kind of dissolve and how effective it's going to be. So just a quick summary. So I've developed this mathematical model of inhibitor dissolution and diffusive transport in water. And then I've developed this time-stepping moving mesh algorithm, so a numerical model to solve that. And we've started identifying some pore characteristics which affect leaching and how that happens. Obviously, I'm in 2D at the moment. So the idea is to kind of try and make the most of working in 2D and learn as much as we can and how that links to 3D. Because obviously stepping this up into 3D is going to be a much more complicated problem. So yeah, we want to make the most of working in 2D while we can. So my next steps are to characterize these meshes for random pore networks and kind of the best way and how that relates to these manufacturing parameters, do lots and lots of simulations and start generating statistical data. And finally, we do need to verify our boundary condition, because again, I'm presuming no transport like through the polymer, and the dissolution rate I don't need to worry about. I'm just using the saturation concentration on the boundary. So we do need to try and verify our boundary conditions just to check. But that doesn't change our numerical model. It just changes what boundary conditions we need to put in. Yeah, we obviously need to get them right, but it shouldn't change the work. So thank you for your time and thank you for listening. Has anyone got any questions?
That was a very nice presentation, thank you. You drew your examples as circles overlapping each other.
Yeah.
Real particles are going to touch rather than overlapping.
Yes, yeah.
Which means that your contact points are inevitably going to be very small. Is this likely to modify what you need to do?
Hopefully not. So yeah, because I'm using circles, obviously we only have one contact point. I have a infinitely small kind of one singular point. If we can't, I think the particles themselves are actually more kind of crystal kind of shaped.
It's still only going to touch at one point typically.
Well, I was going to say one point. I mean, in terms of space, two circles will have a single dot, whereas we're hoping to, if it's got straight edges, if there's a slight overlap or something, it would be where the polymer hasn't completely wet round the surface, you would get a slightly larger.
Mechanical contact theory, it's pretty small contact point.
Okay, so that would be that would change how I set things up essentially. My main thing at the moment has been developing this numerical model, but yeah, when we're doing things like this,
it doesn't impact on what you've done.
Yeah, just what I need to do.
It's just a question of what your boundary conditions are that you're going to assume as you carry it forward.
Yeah, so I mean, essentially it'd be, so we do find there these like choke points, kind of, well, the smaller parts, but if that's the case, then obviously we need to ensure that we only look at places, only where we have small kind of areas, having, well, maybe where I've shown with big overlapping circles isn't particularly relevant. This was more for just developing the model. And then, yeah, I guess going forward, we need to ensure that we don't create those big overlaps.
So first of all, I'd like to concur with the first question. That was a fantastic presentation, and actually one of the best descriptions of the finite element model I've heard for a while. Secondly, I want to come back to the same question, because the question is essentially the difference between diffusion and effusion, and the important point here is the contact point smaller than the mean free path of the particles. Okay. And if that is the case, it means that you can't be scale invariant, because you have to have that mean free path of the particles in diffusion versus the size of the hole through which they're passing. Yeah. And so it's a pinhole problem, and I imagine Patrick had his hand up for exactly the same reason. No, okay, that's good. And I just, could you put that in?
Well, so that's one thing with the boundary conditions. We're kind of presuming there's no transport through the polymer because it would come through here. But I guess once you move back for your pore network, and if they're all kind of only connected by pinholes, maybe transport through the polymer is actually more important. Well, is relevant.
So there's a similar problem in polymers where you swell something with a good solvent called K2 diffusion. And what happens there, you build a stress field. And the stress field, as the solvent comes in, the polymer swells and it builds a stress field, and that limits the rate of solvent going in. So in a similar way that you've done with your concentration, you have a limiting concentration profile. You could do a similar thing with the diffusion through polymers in a K2 diffusion. So it's a really nice idea, really nice bit of work. Thank you.
Thank you.
Oh, second bit. This is my actual question. If you go to where you plot in different lambdas, you plot the different lambdas. 10. Yeah. Aren't these all self-similar? Therefore, doesn't it scale?
Essentially, yes. Yeah.
Right.
The box.
I know, but in your simulation, you want a big box, don't you? So
yeah. So, I mean, it's essentially, I guess you're looking at a localized part of this. I guess the part area would be. This box is the same as that box, but again, I can scale that, and it wouldn't be a problem.
So, are you looking to develop this into other kind of areas? Because we'd be interested. One of the things, it's a beautiful piece of work, by the way. It'd be nice to look at it and look at the polymer the diffusion inside the polymer as well. Because you're 90% of the way there already.
Pardon, sorry.
You're 90% of the way there.
90, okay.
To develop that kind of concentration to a strain field sort of idea. The polymer system.
So it's not something we've thought about, but I'd be very happy to talk about it. So my background is mathematics, so I've very much just been focused on developing a numerical moving boundary model, and I do kind of rely on all you guys to tell me what I need to solve it over. So yeah, very happy to talk about that.
Cheers.
Thank you very much for another question. I also thought it was a really awesome talk, and I love the use of animations in it as well. I think my question is, quite early on in it, you talked about sort of similar triangles as a way to solve an issue with the model wanting to dissolve some of the polymer in as well, effectively, or move outside the space occupied by the salt. Does that mean that every time you do this, you're going to sort of artificially accelerate the edge of the sort of dissolved material as you go sort of along the circumference of the circles in this case here?
So the idea is, so I'm over exaggerating the movement here. I guess there is a potential that rather than, because it doesn't know where the salt is, and it's just saying a certain amount of salt will have dissolved, so I should move over here. If it knew it was limited to where it could move, maybe it would be less. So maybe there is an element that it is moving more than it should be, but because we're using such tiny step sizes, that should be really, really negligible, or at least we hope. Because that's there. I wouldn't be able to think of another way to do it without doing it this way.
Okay, thanks very much, Joe. It's really, really good. I just wait before we clap in. Actually, I just say one comment is. There are two aspects to this model which may need adapting, I think. One is that the particles are treated as rigid, essentially. In other words, absolutely defined, whereas in fact they're more likely to be fuzzy in the sense that there is water within the matrix as well. And the second point is that diffusion of water is maybe 10, 100 times more rapid along that boundary. Yeah. So you'll get diffusion at the back of the particle, but I know you've been adapting the model for those things, but I thought it was a fantastic talk. Thank you very much.
Thank you.